Hello and welcome to session 3.3, Remote Sensing, Satellite Imagery and Data Acquisition Platforms. My name is Aled Rowlands and I'm the Remote Sensing Officer in On-Site Inspection. Now, given my job title, I obviously am a little bit biased to the importance of this session. And joining me alongside me is Franz Ontal, the Chief of Training in On-Site Inspection. Franz will be moderating the Q&A, so please send in your questions to the four presenters we have for you in this particular session. So, like I said, we have four presentations covering a mix of spaceborne, airborne, and ground-based technologies, as well as a spectrum of different sensors and processing techniques. Therefore, without further delay, we will commence with the presentations by Jae-Jun Han on performance evaluation of the pixel object fusion algorithm for change detection in use of countering nuclear proliferation. Now, we will play this as a recorded video, and then we will come to you with questions after we've played the video. So if we could play the video, please. Thank you.
Ms. Nam-Kyung Kim from the Korea Institute of Nuclear Non-Proliferation and Control. I will make a presentation on behalf of Dr. Jae-Jun Han. Today, I'd like to talk about the performance evaluation of the pixel object fusion algorithm for change detection in use of countering nuclear proliferation. First of all, I want to talk about the background of this study. As you can see in the figures on the left on the slide, with enhancement of the spatial resolution, satellite image analysis has been utilized as an indispensable technology to support remote sensing for nuclear non-proliferation, especially in the restricted access areas, such as North Korea. So, for example, non-government organizations such as 38 North and CSIS have observed and analyzed the major or even minor changes to imply suspicious nuclear activities in North Korea. And then here is the question, why do we need a computer-based image analysis beyond human interpretation? Because a computer-based image analysis is necessary to efficiently utilize the rapid increasing number of satellite information. In other words, because of the massive amount of satellite information for interpretation, it is necessary to adopt the computer-based image analysis for supporting the human interpretation. Therefore, since 2019, GAIA has developed the pixel object fusion change detection algorithm, which consists of the following three steps. The first step is pixel-based change detection. The second step is object-based segmentation. And the third step is extraction of the change object. Even though the algorithm can save time and cost for image interpretation, the change detection results can include uncertainties related to governing variables defined by human interpretation expertise, such as thresholds of overlapping pixels. Therefore, the objective of this study is to evaluate the sensitivities or uncertainties of TOP, that is threshold of overlapping pixels, postulated in the pixel object fusion change detection by comparing the traditional accuracy assessment indices such as precision and recall within various TOP values. Prior to that, the area of interest and the process and result of the pixel object fusion change detection were also explained in detail. This slide is about the area of interest, that is Yongbyon Nuclear Complex. The Yongbyon Nuclear Complex has played a decisive role for North Korea's nuclear weapon program. It consists of the 5-megawatt reactor, the radiochemical laboratory, and the uranium enrichment plant. From the perspective of nuclear non-proliferation, the Yongbyon Nuclear Complex, especially uranium enrichment plant, was selected as the monitored AOI. Furthermore, Two figures on the right side were satellite images utilized in this study, and the table is about the specification of satellite images, such as information about sensors, bands, or spatial resolutions. So in this slide, I will briefly explain the workflow of the pixel object fusion change detection algorithm developed by GAIA. As I mentioned above, the algorithm consists of three steps. The first step is the pixel-based change detection using Python. The second step is the segmentation considering multi-temporal images with e-cognition. And the third step is the extraction of the changed object by overlaying the pixel-based change detection results with the segmentation layer using e-cognition. Moreover, there is no pre-processing of satellite imagery step in this study. In the ordinary case, to correct the radial and the geometric distortions, pre-processing need to be performed, such as the Gram-Schmidt pan sharpening and the image-to-image registration. However, since Planet Labs provides the high-quality pre-processed SkySat satellite imagery, no additional pre-processing is required in most cases in this study. From this slide, I will explain the results of the algorithm in detail. This slide is about the results of the pixel-based change detection and the segmentation. The figure on the left side shows the discrimination of the change pixels between images by MAD, which is multivariate alteration detection with a static reliability of 70%. The white on the figure are the changed pixels. Next, the figure on the right side demonstrates the segmentation into image object with similar spectral homogeneity by considering all layers, which is 8 bands of both images. The blue on the figure are the boundaries surrounding image object. This slide is about result of the extraction of the change object by overlaying math with the segmentation layer. In this step, the algorithm distinguishes the change object from the no change object with TOP, that is, threshold of overlapping pixels. The yellow on the figure are the change objects. In addition, I can explain the concept of TOP with diagram in the table. If TOP is zero point 0.5, segment B and C are the change objects. By the way, if TOP is zero point 0.8, segment C is only the change object. Next, we evaluate the sensitivities of TOP to the change detection accuracy. Prior to that, I will talk about the traditional change detection accuracy indices, that is precision and recall. In general, the outstanding change detection algorithm need to be minimized both false positives and false negatives. In addition, according to the confusion matrix, precision and recall is known as change detection accuracy indices to imply false positives and false negatives respectively. Therefore, in this study, to analyze the sensitivities of TOP, precision and recall were estimated in accordance with various TOP values, that is 0.1 to 0.8, where a step size is 0.1. Then, figures on the right side represent accuracy assessment results with 0.5 and 0.8 of TOP values qualitatively. In both images above, positives were the change objects. In addition, the larger TOP, the less false positives and the more false negatives. For true positives, false negatives, and true negatives were determined with the user-defined regions of interest for the actual change object. Moreover, the quantitative sensitivities of TOP to precision and recall in the change detection research is represented on this graph. There is the contradictory trend between precision and recall. In detail, 50% increase in precision and 15% decrease in recall. Therefore, when setting the goal, the change detection algorithm, it is necessary to decide whether to minimize false positives, which is the false detections, or false negatives, which is the undetected. Let's summarize the study. I will talk about conclusion and future work. First, precision and recall were estimated as contradictory with increasing TOP. So, it is necessary to decide whether to minimize false positives or false negatives for supporting remote sensing for nuclear non-proliferation. Second, sensitivities of TOP to the change detection accuracy was investigated as 50% increase and 15% decrease in precision and recall, with the TOP variation from 0.1 to 0.8. As a future work, I will study on optimizing TOP, that is threshold of overlapping pixels. TOP in the pixel object fusion change detection need to be optimized by minimizing both false positives and false negatives reasonably. For example, the reference score, which is the harmonic mean of precision and recall, can be applied and analyzed to the optimization work. This is the end of my word. Thank you for your attention.
Thank you very much for that very interesting presentation, and I'm very pleased that you're using an object-based approach to the classification. I think that's a good way to work on this particular topic. I'm just wondering a few things. You mentioned that you're using e-cognition. Have you brought in or considered bringing in different types of satellite imagery and also vector data to support the classification? I'm thinking primarily here, not regarding a local study like this, but I'm thinking more of an on-site inspection, and in the launch phase to an on-site inspection, where we would have 1,000 square kilometers, and we would try to narrow down the search area, perhaps by using an approach similar to what you just described. So, any thoughts about that particular issue?
Thank you for asking a question about that. Actually, we focused on the local area on the nuclear facility. So we didn't study the 1,000 kilometers squared, but so I think we need to more studies about that. And in this study, we presented SkySat imagery only, but in order to check the applicability of this algorithm, we also utilized worldview, GOI, and concept satellite images. So we conclude that there are minor differences in those research. The algorithm can be used in other satellite images sufficiently. So yeah, I think so.
Thank you very much for that response, and I would encourage you, if you can, and if you have time in the future, to think about how you could apply this technique for on-site inspection by taking a broader scale, if you like, a larger view, and narrowing down the 1,000 square kilometers into something else. I mean, very interesting work. So thank you very much for your presentation and the answer to the question. Thank you very much.
Thank you so much.
This then moves us on very nicely to the next speaker, which would be Elizabeth or Liz Miller, who will be presenting a paper on the Geospatial Automated Imagery Analysis Tool, GAIA, incorporating time series satellite data to detect changing site conditions. Liz, you have the floor. Thank you. Liz, we can't hear you at the moment. Do you unmute yourself?
Okay, hopefully you can hear me now.
We can. Thank you very much.
Great. Now let me share again. Okay, so hopefully you can see the presentation and also hear me. So yeah, thank you for having me today. I'm really excited. I wish I was in Vienna to present this, but unfortunately I'm not, and I'm presenting from my parents' basement right now. So this work has been a really fun collaboration between a couple of labs here in the US, Los Alamos National Lab, Sandia National Laboratories, and Pacific Northwest National Lab. And I'm really excited to be here to share some of our team's work. This definitely was a team effort. I'm the person talking about it, but we have some really great people that were working on it that are presented here in the author list. So like Aled said, I'll be talking about the Geospatial Automated Imagery Analysis, or GAIA toolkit, that our team has built. And this is a great follow-on talk to the previous presenter. So we will continue looking at change detection for changing site conditions. But I want to emphasize that what we're presenting here today is a tool that we've built that is fast-running, low computing power, and really opens up an opportunity for non-GIS users to do some cool change detection analyses without actually needing any sort of background in GIS or image analysis. So with that, let's get started. So an anomalous event detection obviously forces the monitoring community to ask, where did the event occur? And so determining accurate event locations are really critical. We want to, of course, assess site characteristics, any sort of site characteristics that we can. So the nature of the event, was it an explosion? Was it an underground test? The site conditions, so did the event occur somewhere that maybe has a recent history of ground clearing or other site changes? And then also the event's proximity to, say, facilities, infrastructure, stuff like that. But there's a lot of factors like geology and topography that influence the generation of signatures and our ability to detect those signatures. And so these uncertainties can, of course, make event location really difficult. The other thing that happens is that these uncertainties make event relocation really difficult. And so there's a lot of different algorithms that are out there that you can use to calculate, for example, an earthquake epicenter, but those algorithms can potentially give you different results. And so if we look at the figure that's here on the far left, this is just a notional example. So we have 4 points on this figure that represent 4 event locations. And then the circles around each of those points represent a notional error ellipse for each event. But as probably all of you know, the actual event location, finding it isn't quite this straightforward. And so if you take a look at the figures on the upper right and lower right here, these are from 2 different studies that were looking at identifying event locations and then also looking at event relocation. And so particularly the image in the upper right shows a series of event locations in gray, and then the recalculated event locations using a different algorithm in red. And so in some locations, those points are the same, they're consistent. But in many cases, the epicenter has actually shifted a little bit. And in some cases, it's shifted by upwards of ½ degree, which is about 50 kilometers. So that relocation can be difficult too. And so we want to assist with refining event location. And so our team actually set out to determine whether we can use time series imagery to help in some of these analytical assessments. And so as an example, we have 2 images here from the Nevada National Security Site. And so these images show the same aerial extent, but the figure on the left shows the site just prior to a conventional underground explosion. And then the figure on the right shows the site just after that underground explosion. And so obviously you can see that there are some changes that we see that are very obvious in RGB imagery. In particular, for this site, we had some ground staining that was from water that spewed out of the borehole during the test. And so imagery can possibly help refine anomalous event characterizations by reducing uncertainty and helping us see where some of those site changes have occurred. And so ideally, we'd like to use imagery to augment event bulletins with an additional data stream to build confidence in an analytical assessment. And in particular, if we're able to quickly generate these change detection analyses between 2 images, that can be really useful. But the problem is that there is not always consistency in the analysis of those images. And so 2 different image analysts might process imagery different, and so those could lead to different results. And so, our team really set out to build a GIS toolkit that facilitates really important corrections and georectification of imagery in a manner that can then reduce the possibility of user error and decrease total processing time. So the previous presenter talked about kind of the pre-processing of images, and so that's really where we're going with this is doing that pre-processing to set us up for a change detection analysis that standardizes that workflow so that it's the same across the board. And so that's where GAIA came from. So we have our geospatial automated imagery analysis tool. And so yeah, one thing that I want to point out before I move on and kind of show you how it works is that this tool really is meant to be used by novice GIS users who are potentially fairly unfamiliar with how the processing works. So this is something that could be deployed and used in the field in a way that gives you an approximation. It might be a 75% solution, but can kind of move you towards identifying some areas that are worth further investigation. So with that, let's look at how GAIA works. And so I have a video here that will play in just a second, but here's a couple of screenshots for those of you that are familiar with ARC. So it shows you, let me zoom in here. This is what our GAIA workflow looks like. So there's a number of what we call individual tool components or ITCs, and those are essentially each of the steps that you would step through to do your change detection analysis. And so let me play this video, and there is no sound, but I will narrate a few things as this goes. And so our first app was built in ArcMap, for those of you that are familiar with ArcGIS, but we did actually migrate it into ArcPro, which kind of seems to be the direction that Esri is moving and trying to get everyone to use ArcPro. So there's a series of different panes, different layouts that you see in ArcPro here with the map view and the geoprocessing view. And so as this plays, you'll see each of these tool components pop up. And so the ITC 0 is just kind of a README, shows you the general file structure. ITC 1 creates an intersection polygon of each of your raster images. So if you have satellite images that maybe aren't the same extent from year to year or from image to image, these first couple of steps actually make that into the same aerial extent so that you can then do your change detection on those. So that's what you're seeing here is the generation of this what we're calling an intersection polygon, which takes the overlapping area for all of those images. And then all the images are clipped to that same intersection polygon. And then that allows us to do the change detection. And then, let's see, so younger and older imagery with dissimilar extents are cut to an extent where they then overlap. And then this gives us our uniform imagery that we can then do our change detection on, which should be what you'll see next in just a second here. So we create our RGB image. This is, yeah, another step in there. So we create our composite band, and then the next step here should be doing our change detection. And you'll see, so I should point out, this video is about 2.5 minutes long, and it's not, the time is not altered at all in terms of how long it takes for this to run. So it speeds up the processing time. If you were doing each of these on their own, depending on how big the image is, it could take hours. And so this speeds up the process a lot, which is great, and opens up time for other stuff. So here's our change detection here at the end, and I'll get into a little bit more of what these colors mean and stuff as we go. So I'm going to go ahead and move to the next slide here and breeze through a couple of the results. So what do the results look like after using GAIA? And so these two Landsat panels are from Tokyo, and so rather than going back and forth with the human eye, we can let ArcMap do the work and highlight some areas where there's been some change. So let me run through some of these. So here's the results. So this is what the results look like after you run the GAIA toolkit. And so we can highlight some of these really interesting places. So you can see this red box here. You can see a circular feature. If we go back to our imagery, then we can see that there's actually a new building there, and that is something that's been constructed in preparation for the upcoming Olympics. So that GAIA did a pretty good job of highlighting those locations. We also can see another area here, again in the red box, where if we go back to our original imagery, there's been some ground clearing there. But it's not always super obvious to the human eye, and so GAIA manages, or GAIA takes that change and actually makes it a little bit more obvious to the human eye. And then let me run through a few of our final images here. So we wanted to see if we could use GAIA to supplement other international monitoring system data streams. And so in particular, we took a couple radionuclide events that have occurred where there have been some radionuclide detections, and wanted to see if we could use imagery to better understand what was going on around those radionuclide detection stations. And so this is an example from a molten salt reactor that was coming online in China. And so if we look in this area in the red box, we don't see too much change in images from mid and late October. But then if we go to, let me skip ahead just a little bit here. So then if we look at an image from mid-October and then one from January, if we look in this red box again, and then in this blue circle, we actually can see a red, kind of a very distinct red dot here in the middle of this circle. And that's actually a vapor plume that's coming out of the molten salt reactor. So it is now operational, and we can actually see that in the images here. And then one final one that I'll point out, I know I'm running a little close on time. So the other great thing with GAIA is that in locations where maybe our images just aren't great and we can't actually see a lot, we can still run GAIA to get some really interesting change detection analyses. And one of the cool things that GAIA lets you do is that you don't have to just use RGB images. You actually can use any variation of raster bands. And so, for example, our change detection analysis here for the Chernobyl exclusion fires that happened in 2020, we don't see much if we just do a straight RGB change detection. But if we look at what's called the normalized burn ratio, then we do start to see some change. And so this is just a ratio using different raster bands that are available through Landsat. So if we zoom into this area in the blue circle, then we actually can really see where a lot of the burn scars are. So with that, I'll finish up. We have a lot of work that we still want to do to make this a little bit more accessible to people, but the great thing is that it really is, with the drop-down menus that we've pulled in, it really is a really great tool that can be used by non-GIS users to facilitate a quick change detection, which is really cool and really exciting. So with that, I'll finish up, and thanks for having me, and I'll take any questions.
Thanks, Liz. Excellent. So this is a pixel-based approach. I'm just wondering, have you used different spatial resolutions of imagery, and does GAIA allow for different spatial resolutions of imagery?
Yeah, great question, Aled. So yes, the spatial resolution does not matter for GAIA. And so we've actually run it, the examples that I was showing you were from Landsat images, but we have run it on really high resolution data that we have, even just from Los Alamos National Lab. And we've been looking at a low-level radioactive waste disposal facility. And so that has 1 foot resolution, and it runs great. So you can use it with as coarse or as fine of resolution as you want.
So you could throw in as many satellite images as you have available. I'm thinking now of the launch phase of an on-site inspection, which I was talking about before. So you just throw in as many images as you have available without much in terms of pre-processing, and then
yeah, exactly. Yeah, so the one thing that that I should caveat just a little is that where it starts to get a little tricky is that we haven't built in the ability to go from, let's say you had a 30-meter resolution data set and a 10-meter resolution data set. There of course would be some issues there with pixel size and resolution, and you would get a lot of false positives because just because of that resolution difference. So what we haven't built in yet is a step that would essentially resample everything to the same pixel size. But as long as you had imagery from the same platform throughout, if you had 10 images that were all Landsat or any format, as long as they were the same format, then you could just do a series of change detections across those data sets.
Thanks, Liz. Thank you very much indeed. And I mean, I would like to ask all of our speakers to stay online until the end of the session. So if we do have any other questions that come in, we'll ask them at the end of the session. So thanks, Liz, again. So we moved on from spaceborne to ground-based remote sensing, and actually we'll turn to William O'Rourke, who will be talking about unattended ground sensing and in situ processing of geophysical data. And this will be run again as a video. And if we can run that, thank you very much.
My name is William O'Rourke, and today I'm going to be talking about our work towards developing an unattended ground sensor capable of performing in situ processing of geophysical data. There may be scenarios where an unattended ground sensor is your only feasible option for performing geophysical monitoring. However, there are challenges that come with this. There'll likely be no access to the internet or other means to send data. There may also be no power source available to the sensor. Sandia has a long history of developing custom unattended ground sensors for a variety of applications. The goal of our work was to develop a real-time sensing system with data collection for onboard processing of seismic and acoustic data. At a minimum, we would want the system to operate autonomously once deployed without the need for servicing. We'd want it to provide continuous operation using only battery and solar power, provide communication path to allow for command control and data exfiltration capability. It should also have a processing capability to help discriminate between events of interest and other clutter or noise events. We would also want the system to be small and light enough to be human portable. I would like to also note that we are not designing the system to be the final solution, but rather a test platform to show out the concept. The design goal of this platform was to provide an algorithm developer with a feasible system that they could deploy and test algorithms on, using a variety of software tools like MATLAB, Simulink, or Python, as well as providing several hardware interfaces for easy integration with other commercial hardware. With these goals in mind, we are looking at processing boards similar to the Raspberry Pi, as developers can utilize MATLAB or Python or other software to deploy on the system. Additionally, they include hardware interfaces like Ethernet and USB, and also we can utilize the 40-pin Raspberry Pi stacking connector, which provides us more flexibility. The integrated sensor platform, or ISP, shown in the figure to the right, utilizes the PicoZ Zinc 7030 as its processing unit. It also includes an Iridium and GPS modem, a USB hub, a power board, and an ADC board. The ADC board is routed through the Zinc FPGA and provides 8 differential channels for connectivity and a variety of sensors. The power board provides interface to 2 solar charge controllers for 2 batteries and solar panels, which allows for indefinite operation in reasonably sunny environments. The USB hub allows for connection to devices like a Coral TPU for machine learning acceleration, or a cellular modem for additional communication options, or any of a variety of USB devices. Our Raspberry Pi-like stacking header allows for fast and easy integration of a large variety of commercial add-on boards designed for the Raspberry Pi. All this hardware is packaged in a weatherproof Pelican case shown in the figure in the upper right. And the block diagram showing the various components of the ISP is showing the block diagram in the lower right. Sandia has had an active experiment in southern Utah since 2017. The experiment was focused on seismic monitoring of activities at the Redmond salt mine. We were able to obtain logs from the mine engineer of 7 months of data of the blasting that occurs usually at night in the mine. This log contained over 300 blasts with time, mine level, and drift ground truth data. In the lower right here, you'll see the layout of the mine. You'll see the mine has a much longer horizontal stretch than vertical, but the different colors show you the different levels of the mine. There's actually a 5th level AA that's not shown here. We included that because it was in the log later on in our training. The ISP is currently deployed at the Redmond salt mine. We've had it out there since 2018, but it's been under continuous operation since our last visit, July in 2020. Currently, we are communicating with it via cellular. We SSH in and we update code. We pull data. We look for events that our detection algorithm picks up. We also get daily state of health reports via the Iridium satellite communications modem. We get those via email. The system is currently running an STA LTA detector and saving off data and events. The STA LTA detections are then processed by a 2-dimensional convolutional neural network classifier. The system is connected to a trillion compact seismometer. We also run a shadow system locally at Sandia for testing of code prior to deployment to field. So we basically don't want to just upload code there and potentially break the system. So we test it here first, make sure it works, and then we are comfortable with uploading it. One of the things that's nice about the ISP is we can develop algorithms in MATLAB Simulink, which then can be used to generate C++ code and then deployed onto the ISP. Currently, the ISP is running Debian Linux operating system, so it also supports Python. The block diagram here on the left is our simple STA LTA energy detector, which is just monitoring the vertical component of the seismometer. And when it gets significant energy, it saves off the time of the event. And so here you can see that we basically do a simple code generation from Simulink into an application that easily runs on the ISP. Our machine learning work was focused on demonstrating that a machine learning algorithm could be deployed on the ISP, rather than focusing on properly developing or optimizing an algorithm that would perform well in our task. In order to do this, we implemented a smaller classifier that tries to determine in which mine location a particular event occurred. Our goal was to achieve roughly 70% accuracy during training, as we were likely to lose some accuracy during the deployment process from the GPU-enabled workstation to the ISP. Being above the 70% validation accuracy during training would hopefully be sufficient for us to still get decent performance on the hardware. This project will also eventually look into investigate onboard training, but that's out of scope for this work. Our model was a simple 5-layer, 2-dimensional convolutional neural network implemented in TensorFlow 1.5 in Python. The network takes a spectrogram of the time series signal as its input and outputs an array of probabilities, each element of which represents the probability that an event happened in a particular location in the mine. So up here on the top here, top left, you see the spectrogram being input into the 2-dimensional convolution neural network. The output being this 5-element array corresponding to the probability of which level, that being shown on an earlier slide. That would be AA, A, B, C, or D. Gradient steps were calculated in batches of 32 signals using an atom optimizer. We used categorical cross entropy as our loss function. As per our discussion in the previous slide, we aimed to achieve greater than 70% validation accuracy during training. We actually ended up achieving 76% validation accuracy, which falls within our design constraints. Note that the model is trained using quantization nodes in accordance with our desire to deploy on the hardware. And so back to the hardware itself utilizes a Coral TPU, which requires a quantization step of the model in order for it to be able to run on the hardware. In general, the model seems to train well, meaning the data is likely separable. The validation curve is significantly noisier and does not achieve the same accuracy as a training set, leading us to believe there is greater regularization that we can do to further improve our model's generalizability. The plot to the left here shows the training and validation curves, the training being in blue and the validation being in orange. We would really like those two to match up a little better, but they don't. However, we're not focused on our model performance, so we're accepting this overfitting. Also, when comparing our model performance to the SNR, the signal on the right, the plot to the right, you can see that our model roughly does better when the SNR is higher, which is logically what we would expect. In conclusion, we've developed a custom unattended ground sensor capable of remote and autonomous operation. We have demonstrated a semi-complex machine learning model running on the system. As expected, we saw a reduction in performance when we quantized the model to run on the Coral TPU. The result was our validation accuracy dropped from 76% to 52%. Some of our future work in the short term, we'd like to demonstrate event association across multiple spatially separated units on the order of 5 to 10 kilometers. We'd also like to explore ways to overcome the drop in performance due to quantization. In the long term, we'd like to identify one or more candidate algorithms with real-world use for implementation on an ISP, something like earthquake versus explosion detection. We'd also like eventually to attempt to train the models on the ISP. So for example, if you were deployed at a location where you knew there was mine blasting and you could identify that in the data, you could then tell the sensor by labeling the data to train itself to ignore that or maybe not report that. And that is the end of my talk. Thank you very much.
Thank you, William. Thank you. Very interesting presentation. Again, I'm going to talk about on-site inspection. My question is going to be an on-site inspection again. We deploy a lot of unattended equipment, seismometers, and various other samplers, environmental gas samplers, and so on in the field. And your last but one slide spoke about communication between different units, and I'm just wondering, would the data processing then take place on a solitary device? So you'd gather the information from the different sensors and then send them via cellular communications to a single device in the field. Is that the plan?
That could be one of the ideas, maybe more of like a central processing type system, or another option is, the Iridium sends email messages. You could do the aggregate processing like in the cloud platform or on a host computer back at your facility.
Yeah, it's very interesting. And I think this is the way that we currently do things in on-site inspection is that we would send the data, the raw data, via telemetry, via a base station back to our base of operations, whereas we wouldn't do the processing in the field. And your approach is interesting, and I think we will have to think about this as a possibility as well, and it's very interesting. So thank you very much indeed, and please stay online. If we do have any other questions, we'll come to you at the end of the session. Thank you very much.
Absolutely, thank you.
So finally, the last presentation, we go again a little bit airborne in this case, and we turn our attention to commercial UAV-based magnetic field mapping solutions, and we'll speak to our former colleague, Li Peng. Li, you have the floor, sir.
Hello, dear colleagues. I'm Li Peng from Hope Investment Development Corporation of China. First of all, it would be our great pleasure to be selected to speak in this very important Science and Technology 2021 meeting of CTBTO. This work would be a joint effort by several corporations. The first one is Hope, second one is Hong Kong Technology Guangdong Corporation of China, and third one is Beijing Institute of System Engineering. So I'm speaking on behalf of the whole team. We hope that our findings, our work could contribute to the development of the on-site inspection verification regime. My introduction would be composed of three parts. The first one is technical background. Second is system illustration. The third one is application scenarios. First part, technical background. As we all know, magnetism exists everywhere. With the detection of magnetic anomaly, it can find mineral deposits, pipelines, buried infrastructure, unexploded ordnances, etc. Magnetic detection reveals the potential truth of nature and tells us the real image of this world. Take into consideration of the CTBT scenario. In the treaty language, CTBT treaty clarifies to apply magnetic and gravitational field mapping, ground penetration, radar, and electrical conductivity measurements at the surface and from the air as appropriate to detect anomalies or artifacts of the CTBT. If we look at the recently developed very important document of the PTS of on-site inspection. Magnetic field mapping equipment, both at the surface and in air, have been listed on the first comprehensive draft list of equipment for use during on-site inspection. So we can see that magnetic detection will be very important for the conduct of on-site inspection in the future. Based on the lessons learned during the past training and exercise experiences, especially in IV-08 in Kazakhstan and IV-14 in Jordan, inspection efficiency and health and safety concerns are very important factors for conducting surface or air magnetic field mapping. Our system, here we listed the core technologies. We have four core technologies: multi-rotor UAV. Second one is quantum magnetometer. The third one is automatic magnetic data processing and visualization. The last one, but not the least one, is for drawing 3D digital map. Second part of my presentation will be system illustration. Before I jump into details, I would like to provide a short video clip to give you some general introduction to the system. Okay, from the short video clip, you will see that the system composition will be quite clear. First is a multi-rotor UAV with a magnetic detector. And second would be a same platform, but with different payload. That is a 3D camera on board the multi-rotor UAV. All the data gathered by these airborne platforms will be transmitted through antenna to the ground station for data processing. And we have another chart to introduce in more detail of the working mechanism. For this chart, we will see some of the hot spots of our system. The first one, of course, is a UAV platform, and then data will be transmitted in real time to the ground station for processing. So this will provide more computing power and more capacity for data storage. And also you will see both the magnetic data and the GIS data will be shown vividly through colorful maps instead of just the plain data. To come into detail, the first element of the system is multi-rotor UAV, which can carry different payloads for multiple operations, such as magnetometers or 3D camera for on-site inspection. And the maximum payload would up to 10 kilo. An essential element of our system, of course, would be cesium magnetometer. Compared with the previous magnetometers, quantum magnetometer has better detection sensitivity, which can be up to PT level, with great robustness. Cesium magnetometer is one of the quantum magnetometers. It can be small enough to be carried on several platforms. The combination of UAV and cesium magnetometer would be an innovative technical attempt. The weight of this sensor would be within 2 kilo. This chart is a chart for showing the basic working principle of our sensor, the sensor of cesium magnetometer. In simple language, it's based on quantum theory, and the magnetic field will have its effect on the output frequency of the sensor, so we can get to the measurement through this way. The 3D camera carried by UAV, this camera is able to capture images and position information in the air. And then with the software processing, the raw data of 3D camera is able to construct real 3D model automatically. In the case of OSI application, it's very useful for the comprehensive understanding of the target area, which will be helpful for inspection planning. The weight of this 3D camera is within 1 kilo. Then for data processing software. Data processing and visualization would start right after data acquisition. Magnetic forces would be illustrated instead of in the form of wave curve, but colorful 3D map, which is much easier to show magnetic anomalies in the inspection area. The last part of my introduction would be application. Actually, we have done several tests for this system. In 2020, an exploded audience detection test was made. For a 50 kilo UXO device, the system is able to detect its existence and the location at a distance of 4 meters. In the early time of 2021, vehicle detection test was made. For an ordinary vehicle, the system is able to detect its existence and location at a flying height of 50 meters, which will be greatly useful for debris flow recovery, sank vehicle recovery, etc. In the summary, in simple language, flight endurance of the UAV could be within 1 hour, a maximum payload 10 kilo, maximum speed 20 meters per second. Sensor sensitivity could reach to 0.6 pt. The sensor weight within 6 kilo. We have two dual-mode GNSS antenna, which is adaptable to GPS and BETO. Maximum 3D image resolution would be up to 2 centimeter. 3D map data is geo-referenced, and the magnetic detection resolution could up to 5 centimeters. Thank you very much for your attention.
Lipeng, thank you very much indeed for that very interesting presentation. This is something that has taken our attention over recent years as well, and we thank you very much for your presentation. The idea of having these things is interesting. Have you ever considered swarming these things? We have multiple drones and multiple detection units, i.e. magnetometers in the air, simultaneously in order to increase the coverage of the mapping survey area?
Yes, I think it's a good question. If I understand correctly, you want to integrate all the sensors together, right?
Not quite. I was thinking of if you have a large area to survey. I mean, we're talking now about 1 hour duration. Presumably that drone can land, that platform can land. You replace the battery and it can fly off again. But if you're under time pressure and you had a relatively large area to survey, whether the base station could cope with, for example, flying with 2 or more platforms, so you cover a larger area during your survey then?
Okay, this is a good question. Probably one of the solutions you already mentioned is that we can utilize several platforms instead of just a single one. And another one, probably we can use a bigger platform, probably a manned helicopter instead of a multi-rotor UAV. So in that case, we can have a bigger sensor. It's something also something under planning within our team. It's a good direction for the next step.
If I understood it correctly as well, the data from the sensor and on the platform was being transmitted directly to a base station during flight. Did that include the magnetic data, or was that information only about the trajectory and of the platform itself?
I understand you are correct. As both the data for controlling the platform, flying platform, and also the very useful data, both for magnetic and GIS data. So all the data will be transmitted to the ground stations, either for control the UAV platform, but also for data processing, magnetic data and GIS data.
And just one final question then, regarding the platform itself. The flight plan was pre-programmed. There was no human interaction at all during the flying. It was all pre-programmed. Is that correct?
Yes, you're right. And also we have a UAV pilot, which can control the UAV. So we can do it in both ways.
Okay. The thing which is of interest there is because this sensor, this platform and the sensor attached to it, they're flying pretty low to the ground. And if there's minor topographic changes like a mound of rubble or whatever, you would need to have an operator there to adjust the flying height of the platform, or presumably you could have a sensor allowing it to adjust based on the distance between the object, between the platform and the ground. So I guess there are lots of opportunities there to look at that as well.
You are absolutely right. We have a sensor which can provide the capability that the platform will avoid collision with obstacles. Yeah, and you are also right that the terrain of the ground area probably will be challenging. So in this case, we definitely need automatic piloting system instead of man in the loop.
Thank you very much for the presentation and the answers you provided as well. We have come to the end of our allotted slot here. I'd like to thank all 4 presenters for their presentations today. It was a very interesting set of presentations. I'd also like to thank Franz and the technical team here in Vienna for this session. And I would like to bid you a good day from Vienna. Thank you very much.
Thank you.